There are three types of mechanical looseness in rotating machinery. Type A looseness is related to a lack of sturdiness in the foundation, base plate, machine's foot, or some ground settlement. Via spectral analysis, it's possible to identify this condition by a vibration peak in the first harmonic. Whereas type B looseness occurs due to loose bolts, cracks in the pedestals, or in the bearing itself. Unlike A, the shape of this looseness in the spectrum is a time wave of 2 pulses per rotation. That is, for every half rotation frequency, there's also a certain level of floor noise. And type C looseness is generated by poor fixation between parts that compose the dynamic forces of the rotor, also referred to as internal looseness. Some examples are an improper fit between the bushing and bearing housing, between the bearing inner ring and shaft, between the outer ring and bearing housing, or looseness in the coupling flange connecting elements. So, with the action of the dynamic forces of the rotor, nonlinear effects arise, and then subharmonic and interharmonic components will appear. So when we observe the spectrum of type C looseness, they present several peaks up to the 10th harmonic. Machinery misalignment is extremely common in rotating assets and is typically the root cause of machine failure. It causes excessive wear that leads to premature failure in components such as couplings, rotors, bearings, seals, and mounting plates. For example, an industrial seal failure can cause an oil leak and the machine stoppage. An excessive vibration in the fixing screws can also occur, causing a structural problem in the equipment. And there's also the energy consumption issue. Observing these charts, we can see the increase in energy consumption as your misalignment problem advances. In the case of severe parallel misalignment, you can reach an increase of up to 10% in energy consumption.